and thank you very much for this invitation. And I know that this is the third day, I suppose, right? Third or fourth day?
Fourth.
Fourth day. Okay. So a lot of things have been already covered, and I'm not quite aware of what all the things are covered and all that. So there may be slightly repetition, and somebody can interrupt and tell me that you don't need this slide, so I will move on. Right. So let me share the slides, and I may not be able to see the chat box during the presentation. So if you have anything to ask me, just unmute and ask. Otherwise, let us wait until the end of the session, and then we can discuss. Yeah. So let me just see how can I share it here. Yeah. Yeah, I hope the slides are visible. So
Yes, sir. Yes, sir.
yeah, so let me continue it. And as I told you, you can interrupt me, but I may not be able to see the chat box. So you please unmute and let me know. Yeah. So the title of the talk is Deep Neural Architecture, some from algorithm to applications. But in this particular talk, I think I have removed a lot of the algorithm part of it, assuming that a lot of has been covered. But just for your completion of the talk, etc., I have a couple of slides which talks about the deep neural network algorithm, the architecture, etc. And then we move on to two applications which we recently worked on. In fact, both of them are in work in progress. We have not yet published, but that's okay. So let's discuss that. So as you know, I mean, some of the machine learning basics, I think I was, I think a week back or something. So somewhere I was giving a talk, and then somebody asked me whether machine learning, deep learning, they are the same or they are the different. Now, deep learning also started as a machine learning tool, but as you know, it's now outgrowing machine learning actually. So deep learning itself is becoming a kind of a subject by itself or a domain by itself, and it's becoming, I think, instead of becoming a subset of machine learning, now it is becoming a kind of a set by itself. If you remember, when computer science started, it started as a branch of mathematics, as a branch of electronic sciences, as a branch of logic, but electrical engineering. But slowly, computer science has outgrown those subjects, and now it has become its own. The same is true with the deep learning also. So machine learning is a field of computer science that gives computers the ability to learn without being explicitly programmed. In fact, I don't have that slide, but I can tell you what happens in case of normal programming is that you give the program, you give the data, that is the input, and the computer will find out the output. But in machine learning, what happens? You give the input, that is the data, and you give the output, what you want from the data, what you learn from the data. And then this system, this machine will learn a model, a program. So it will create a program, a set of instructions or a set of weights, so that given the input, it will try to learn how to produce the output. Now that's a paradigm shift in computer programming. Like in the standard traditional programming, we give the input, we give the program or the instructions, it will generate the output. Now in case of a machine learning, we try to give the input, we try to give the output also, and the system learns how to generate the output from the input. So the program will be generated, the instructions will be generated. So the diagram shows that there is a level data. Level data means this is the data and this is the output. So level means you have already leveled that data, and the machine learning algorithm will learn it. So it will create a model that is called the learned model. Now, so the machine learning algorithm will create the model. So this model is basically the program. Then you give unlabeled data. So this unlabeled data means you give a new data set. You don't know what is that, but because the system has already learned it, it will be able to predict. And that's a simple logic. Now, what is machine learning and deep learning? I mean, that's how we started. A machine learning subfield of a learning representation of data, exceptionally effective at learning patterns. Now, I think instead of leading the test, now let us look at this. You give let's say I give an input, let's say it's a car, And what we do, or what another program does, is that it tries to find out the features. Once the features are extracted, for example, there are 4 wheels, the color is red, there is a steering, the size is this much. So you extract the features. Now these features are given into the model, that is the machine learning model, whether it's a neural network, whether it's an SPM, whether it's a KNN, whatever model you are doing, and then the output will be obtained. So the output will be either it's a car or it's not a car. That's a standard machine learning model. But deep learning, I think it goes one step ahead and allows us not to extract the feature, because I don't know what are the features. Let the features also be extracted by the system automatically, and that's what deep learning does. So in the deep learning, if you look at this feature extraction phase is not here. So you give the input, and the deep learning will extract the features, you don't know, the automatic features, and then it will classify and try to find out whether it's a car or not. This is the, I don't want to say that this is the only difference, but this is one of the fundamental difference in deep learning and machine learning, that you don't have to worry about the feature extraction part. Why deep learning is useful? I mean, there are many things that you can do with deep learning. In fact, these days, every application has a component of deep learning, actually, right? Whatever applications we have done, image processing, speech recognition, voice synthesis, network traffic generation, and all that stuff. So everything is now you can add with deep learning. And now I see that every paper which talks about deep learning, the success rate or the accuracy is almost greater than 90%. So earlier people are struggling in the zone of 75 to 85. That was the accuracy zone. And now everything is between 90 to 95, 96, 97, etc. So that's the beauty, or that's the power of deep learning. So from 2000, if you look at the last line, from 2015 onwards, deep learning started outperforming the ML techniques, first in speech, then in vision, and then many others. Almost every area they have now, trespassed into that. So what are some of the features? I say it is easy to adapt and fast to learn. It is not exactly fast to learn, but it is easy to adapt, definitely. Fast to learn in the sense that once the learned features are there, it is fast to learn. And we'll also discuss about that a bit. Deep learning provides a very flexible and universal approach. So that's very important. Now, it is an effective end-to-end joining system. Like, we are not talking about feature extraction, PCA, independent component analysis, principal component analysis. We are not talking about those things in the deep learning sense, which are normally the terminology used in machine learning. But in deep learning, we try to move ahead of that, go ahead of that, and say, okay, everything is universal. Just give me a data and let the system learn on its own, extract the features on its own, and all that. So what exactly is deep learning, and why it is generally better than the other methods on images, speeches, and certain other types of data? It's not always true with all types of data. Multi-layer neural network have been there for around 25 years, I think quarter century. But what actually is the new thing here? So deep learning means using a neural network with several layers of nodes between the input and output. That's the first definition, that instead of 1, 2, 3 hidden layers, we have many hidden layers between the input layer and between the output layer. So there is a deep, layers. There are many layers in between the input and output. So that's the first thing. Now, the series of layers between the input and output do the feature identification and processing in a series of steps, just as our brain seems to be. I repeat, brain seems to be. Not necessarily that the brain does like this, but that is what is our understanding as of now. The brain also does in different layers. The brain does a function in different layers. So this is a layered architecture of neurons, and that architecture tries to mimic the brain little more than the neural network does, actually. Artificial neural network does, actually. But the only point I want to make it here, deep learning is much more than multi-layer learning. It's not that only there are multiple layers or there are many layers, so that is why we call it deep learning. It's much beyond that, actually. So we'll see some of them in the next class. So a multi-layer network, as I told you, it has been there for quarter century. What is actually new? So we have always used you had a good algorithm for learning the weights in network with one hidden layer. That's there for almost 30-40 years. You have input layers here. There is one output layer, and there is one hidden layer. And you have many learning algorithms which are good for training them. But these algorithms are not good at learning the weights of the network with more hidden layers. When the number of hidden layers are more here, then what happens? Your learning algorithms, what you know what you know in artificial neural network, etc., they are not pretty effective, they are not pretty good, they are not very easy to learn. So the problem is that what is new is that in deep learning neural architecture or deep learning architecture, one of the new thing is that the algorithms for training many layer networks, sorry, it is this is Y actually, it's not T, many layer. So many layer networks. So when you have many layer networks, the learning, the way we learn in case of an artificial neural network, the learning in many layers is slightly different, and I think it's much different, and that is another thing. So point number one, it consists of multiple layers, many layers, but that is not the only new thing. Point number two, the algorithm to train the multiple layers are different than the algorithm that is trained used to train the single layer or two layers or three layers. A simple neural network, anyway, we know, you give it this. Suppose I have okay, let me go back. So we have input layer x1, x2, x3, x4. Let's say that these are the four variables. The dimension is 4. Then I have an output that is y. So I'll give you this x1, x2, x3, x4 at the input, and my required output is y. I'm talking about this supervised learning. Now, if this is the case, what is I have to create a black box here. Now, this black box is my neural network architecture, and this black box will give me y here. So what do you do here? You create some hidden layers. Let's say the hidden layers are A1, A2, A3, A4, one hidden layer, and there is another hidden layer that is called A5, and then we have these connections. And this is what we know anyway. So x1 is connected to A1, A2, A3, A4. These are the four neurons in the hidden layer. Similarly, x2 is connected to all the four. So how many connections are here? If you look at the connections, x1 has 4 connections, so we'll have 4 weights. x2 will have 4 weights, x3 will have 4 weights, x4 will have 4 weights. So total 16 weights are here, right? Now these are 4 here, and there is 1 here. So 16 plus 4 plus 1, 21 weights are there if there are 4 inputs and 1 output. I mean 4 input variables and 1 output variable. Now, if you look at this, I mean, this is the formula. I can always leave it. So how do I calculate A1? I calculate A1 x1 multiplied by W1, then x2 multiplied by W2, and so on and so forth. So you calculate this, take the sum of these things, and people are using either I mean the sigmoid function or this ReLU function, ReLU function. ReLU function is anything you can do. Suppose I have a function like ReLU, I define it as a max of 0 and x. So what does it mean? It means that if it is negative, you take it as a 0, or if it is positive, you take that positive the quantity. So this is basically between 0 and 1. So negative is truncated here. That's okay. So you get so how do if I use ReLU function here, then what is the function? So you take the maximum of, suppose you take the ReLU function here or here, wherever it is. This is the ReLU function. So you take the maximum of 0 plus this value, and you try to find out that. Again, that is not very important. This is also a standard neural network architecture. And then you find out this is the summation you get, and you use this sigmoid function or some function, or we call that as a softmax function, and you find out the value of y. Now, suppose the y, what you get from here, because the W1, W2, W3, etc. randomly generated, the value of y, what you get here, and the desired y are not same. So you find out the difference, the error, the loss function, and using the loss function and the kind of a learning algorithm, you try to modify the weights, update the weights. And these updated weights, again, you submit another set of x1, x2, x3, x4, find out another y, and this continues until the weights learn. Now, let us see. So as I told you in the last slide, there are 4 into 4. There are 16 weights here. There are 4 weights here. And there is a 1 weight here. So 4 into 4 plus 1. So there is almost 21 parameters. Now, if you look at an image, suppose I want to train images and all that, what will happen? An image size is, I mean, it's a standard image size is, or I mean, not even a standard actually. Let's say there is an image which has 400 plus 400 plus 3. What is 400? 400 rows, 400 columns, and 3 RGB, red, green, blue, three things. So this is the input size, 400 cross 400 cross 3. Now, if this is the input size, now look at this. So how many inputs are there? x1, x2, x3 up to x 4,80,000. Because 400 into 400 into 3 becomes 4,80,000. So your input size becomes now, instead of 4, now it is 4,80,000. Now if you look at an hidden layer, even if there is only one hidden layer, now you see this is the output. So how many parameters you will have? 4,80,000 this side, then this is 4,80,000. So 4,80,000 into 4,80,000, that is what is the number of weights in this place. And then you have 4,80,000 because these are 4,80,000, so that will be 4,80,000 weights here plus 1 here. So that is approximately 230 billion weights. Now, can you imagine that 230 billion variables, the variables or identifiers will have to be trained, will have to be updated, will have to be learnt, so that you give the value of x1, x2, x3 up to x 4,80,000, you get the corresponding y. Now, this is too much actually. This is too much in the sense that training 230 billion variables in one single layer. And if you go for deep neural network, then that's a big problem actually. So I'm trying to tell you that what is the complexity of the deep neural network architecture and why the architecture is more important, because you just can't put as many as number of layers in the as many as number of neurons in the hidden layer. That's not allowed. I mean, that's not advisable, because you have almost 230 billion weights in this simple example. And if it is or some other example, you may go for some 100,000 billion weights or something like that. So that's not allowed. So what do you do? One immediate thing what you do is that instead of putting 4,80,000 neurons in the hidden layer, we make it, let's say, some 1,000, only 1,000 neurons. Now, what is 1,000 neurons? That means from 4,80,000 input variables, we will extract only 1,000 features. So this 1,000 neurons are basically represents the 1,000 features from 4,80,000 actual data. So if you reduce it to 1,000 only, if I reduce it to only 1,000 neurons instead of 4,80,000 neurons, then the number of weights, the number of variables you need to learn is now coming down to 480 million. But that's also a big number. So, but from 230 billion to 480 million is a drastic reduction actually. Okay. So the whole idea is that this is a famous quote actually. Deep learning doesn't do different things; it does things differently. So it will do the same classification, it will do the same clustering, it will do the same recognition, it will do the same identification, but it will do things in a different way, in a better way actually. Now the new way to train, actually what was happening earlier is that I give the input here, I get the output here, and I find out the error function here, the loss function here. Then I try to train everything at a stretch. That was the standard traditional algorithm. But now what you are trying to do is, this is the difference. We train these two layers first. Once the training about these two layers are over, then you go for the next layer. 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 So this is how the other difference between the training of a multi-layer neural network and a deep neural network is that in a multi-layer neural network, all the layers are trained in one iteration. But in case of a deep neural network, only two layers at a time. I mean, the first two layers, then second and third, then third and fourth, they get trained and then they move forward actually. So that's one of the difference actually. So basically what you do, each of the non-output layer is trained. So this is the output layer. So each of the non-output layer will be trained. And then once they get good features, so this is the first level features, this is the second level features, this is the third level features, fourth level features, so on actually. So if you look at this, the number of input neurons or the input layer is more, and the hidden layer we reduce the numbers, just a representation actually, we reduce the number, and in the output layer again you can reproduce it and you do whatever you want. Let's say okay, this also I can skip. Okay, so this is basically a performance related thing. You might have seen this graph also. It's a very popular graph. I borrowed it from Wikipedia only. So when you have more number of input data, then the traditional machine learning algorithm will also be performed good. But the only thing is that they perform well until a particular point, and then they flatten. The curve flattens here. So the performance of the traditional machine learning algorithm increases with the increase of data, but soon they come to a plateau. They become flattened. But in deep learning algorithm, if you give more data, more samples, more input, more training data, then the deep learning algorithm seems to be performing better, and the performance also increases beyond a particular point. I mean, it goes on. More the data, the accuracy becomes better actually. So that's another important point, that if you have more data samples, more training data sites, then deep learning is much better. But if you have less, then probably deep learning is not more. For example, if you look at this part of the graph, now you see a traditional machine learning algorithm like ML and other things will start doing better immediately. Look at the blue curve here. They are still better, and the performance is better compared to deep learning in up to a particular size of the data. Beyond that, deep learning seems to be better. So one more takeaway here, that you must have more data samples for training, then only the deep learning is better. Otherwise, it's not supposed to be better actually. So okay, this I think this is the this one. Okay, fine. So the deep learning has an inbuilt automatic multi-stage feature learning process. That's what we have been talking about. Every layer extracts a feature, and this is automatic, that learns rich hierarchical representation. For example, you give an image, it will extract the low-level features, then middle-level features, then high-level features, then trainable. In fact, if you look at this diagram, so first it finds the edges, then it finds the texture, then it finds the color, then it finds the shape, and then it tries to classify it whether it's an outdoor environment or an indoor environment, or whether it's a bedroom or a drawing room or a toilet, like that. So what happens actually, you give it as a pixel. I just give them as a pixel. My different layers will find out. That's what I was telling. The edge, the texture, the motif, the part means the objects there inside the thing, and finally I try to see what is there in an object. Now I give you one example. I think that's a very famous example. Now suppose your system is trained to recognize dogs. Now there is a picture, a family picture, but the dog is also part of that family picture. Now you want to identify whether the dog is there or not. So what you do, we are not giving the features of the image here. You are just putting the image. These are the pixel values. Then different layers of the neural network, I mean deep neural architecture, will extract different features. One layer will extract the level, I mean the edges. Another layer will extract the colors. Another layer will extract the shapes. And slowly you will find out that one particular layer will be able to identify the objects present there. There is a dog, there is a wall, there is a fan, so this is also one level feature. So the features from lower level to higher level, when they go from one layer to the other layer, they get those features, and finally those features can be combined together to get the ultimate output. So each module in deep learning transforms its input representation into a higher level one. So in a way, similarly, so this is what the human psychologist or the physiologist has found out, that human cortex, when you look at an image, etc., human cortex seems to be doing like this. So there are a couple of papers which says that the human beings learn like this. They learn in layers actually, and that layered architecture is borrowed into the deep learning. Now, I think let me have another 3 slides on deep learning, and then I move on to the applications. So one of the standard, very popular, very useful technique is the convolutional layers actually. So how a convolutional layer helps? Now, what is convolution? Now you take an input image, let's say A, B, C, D, E, F, G, H, I, J, K, L. And if you have already seen this diagram, maybe you can ask me. But otherwise, quickly, I will take 2 minutes only to explain this. Now what you do, you take a filter. Now what is this filter? This filter is basically trying to say that what type of features you are trying to extract. Are you extracting edges? Are you extracting color? Are you extracting texture? So based on that, there are different filters. Now, I tell you, people work in a different ways in deep neural network architecture. One is that people work on deep neural network only, and some people work on deep neural network applications. So for example, I don't work on deep neural network, the algorithms of deep neural network. Rather, I work on the application level of the deep neural network. Now, people who are working on the deep neural network, one researcher can come out with that, what should be this W1, W2, W3, W4? One researcher may say W1, W2, W3, W4 is 1, 0, 1, 1. Another fellow says, no, 1, 0, 1, 1 is not a good feature extraction. Let us put it 1, minus 1, plus 1, minus 1. So, and then they exploit the entire algorithm. They test with the benchmark data, and then they find out that their results are better than the existing results, and so on and so forth. So how it works actually, how the filter works, you take the W1, W2, you take a 2 by 2 window, because this filter is 2 by 2. You take a 2 by 2 window and then calculate A multiplied by W1, B multiplied by W2, E multiplied by W3, and F multiplied by W4. This is this. And then you can use some functions, whatever function, whether it's a modulus function or whether it's a max function, whatever function. And this value is now H1. This H1 is here. So you put this. you put this, then you move the window. Now this the filter window is moved to BCFG. Same logic, calculate B multiplied by W1, then C multiplied by W2, then F multiplied by W3, then G multiplied by W4, use a function, and now this becomes H2 because this moved to the right, so this is now H2, so on. So you apply a filter on that image, and after you apply the filter, you get new values H1, H2, H3, H4, H5, H6. So now this image is convolutionized to form a new thing. Now this image is now converted to another thing, and that is a new type of feature. So this H1, H2, H3 will give a new type of feature. So this is a feature map. If you look at this is a feature map. So number of parameters for one feature map is 4 here, and the number of parameters for 100 feature map is 4 by 100 actually. That's how you go ahead. So if there are 100 layers, you multiply by 100. Now this is how the one example of a filter is a 3 by 3 filter. The number says that 0, 1, 0, 1, minus 4, 1, 0, 1, 0, etc. So if you take this image, apply this filter, so the filter will go on like this, and then finally you get an image like this. So why you are getting this image? Because these values, these RGB values, these values of the image are convolutionally changed using this filter, and it has been proved, or it has been shown by the researchers, that this filter gives me a kind of an edge, a black and white edge. So I'm not worried about now the original image. Now I'm worried about this level of image, so on and so forth. So there is a paper by Hubel and Weisel in 1962, and they say they were not working on deep neural network, they were working on vision cortex and all that. So they wrote this paper back in 1962, and people borrowed that idea from that paper from 1962 and started using it in deep neural network. Now let's say, so this is the same thing, right? So you have an image, you have a filter, you get first level. Then in the first level, so you move this one, it goes like this. Then in the second level, you use some other filter. Let's say W5, W6, W7, W8. The weights are different. Then you get second level features. Then here, again, you use something, and then it goes to the third level feature. Now this is, so applying a filter to that data set is the first level of feature extraction. The second level of feature extraction is called max pooling. So max pooling or average pooling. Now what is max pooling? Now look at this. Suppose you have after this feature is extracted, the input is now this. So 4, 1, 3, 5, 3, 4, 2, 3, 1, 3, 1, 1, 3, 0, 1, 0, 4, etc. Now what is pooling? Pooling means you define a window. Now this window is a 2 by 2 window. Let's say this is the window. Now in this window, what is max pooling? Find out the maximum value. So max pool of a 2 by 2 filter with a stride of 2 is, now look at this. So between this window, you get 4 at the maximum value. In this window, you get 5 at the maximum value. In this window, you get 3 at the maximum value. And in this window, you get 4 at the maximum value. So now the max pooling techniques reduces the image, or reduces the images to another 2 by 2. So in this case, a 4 by 4 matrix is reduced to a 2 by 2 matrix using a max pool function with 2 by 2 filter actually. Now if you use 3 by 3 filter, you will take 3 here, like that. Now some people say that, why do you take max pooling? Why don't you take average pooling? So same thing, you take these 4 values, take the average of that. That's one model. Very recently, I saw one paper where they say stochastic pooling. What is stochastic pooling? They say that, look, you will let us push some kind of a randomness into that. Stochastic means random process. So instead of taking max or average, pick up a number randomly, pick up a value randomly between that point. So this 1, 3, 2, 4, one random value pick up. It may be 3, it may be 2, it may be 1, it may be 4. Some people say the random stochastic process will also be weighted stochastic process, because the probability of picking the highest value is more than probability of picking the lowest value. So generate a probability and pick up a value. So many types of pooling technique people are using, and that technique will try to find out another feature vector here. So it goes on. So the convolutional neural network looks like this actually. I mean, this is probably, how do you do it actually? I mean, this diagram, people who have done deep neural network or people who have attended classes might have seen 100 times. It's a standard diagram picked up from the Wikipedia and the other paper actually. So if you have an image, it will go through multiple layers. In some layer, you extract the feature. That means you reduce it by applying the filters. Then you, in another layer, you go for max pooling. In another layer, again, feature extraction. So it goes like this. Now, after all these things, now what is the challenge here? The challenge here is that, how do I know? Now, as I told you, in deep neural network architecture, why I said it is architecture, because it's like a computer architecture. It's a computer by itself. It's a system by itself. There are so many layers. You don't know how many layers are there. How many layers are optimal there. How many layers are good there. So you say that I will go for 25 layers. Somebody says I will go for 50 layers. Somebody says go for 75 layers. How do you decide how many layers you will take? Number one. How do you decide in each layer how many neurons will be there? Number two. How do you decide which filter function will be used? How do you decide which pulling function will be used? Pulling function will be used. How do you decide which learning parameter will be used? How do you decide which activation function will be used? And because there are so many layers, because there are so many neurons, etc. My problem is that how do I decide on this? Now, deep neural architecture determination is very, very difficult, and it's not easy for a starter, who starts the research, etc., to fine tune. And in every architecture, there are billions of parameters to be tuned. So your years and years will be wasted until you find out what is a good combination of a particular network, so that you get the better result or better performance. So that's the first thing. So deep neural architecture determination of the deep neural architecture is difficult. It involves millions, sometimes billions of parameters to be tuned. Researchers, now what is, there is a saying called ki you should stand on the shoulder of a giant actually. Many researchers, those who are deep into the deep neural architecture research, they have worked on the architecture. That means they have found that what should be the number of layers, how the layers should be treated, which filter will be used, etc., and suggested few already trained deep neural architecture. For example, AlexNet, VGG19, ResNet 50, MobileNet V2, Inception V3. There are so many. So what is this? Let's say Inception V3. Now, Inception V3 is an architecture. So when you say Inception V3, this model says, I don't remember exactly how many layers, etc. This model says that these many layers will be there. In each layer, these many neurons will be there. In each neuron, these are. This is the way the training should be done, and all these things have been done. They tested with some benchmark data sets, because benchmark data sets are anyway there: images, voices, speech, all these things. So they test with some benchmark data set, and they report that this is my best result. So we got the best result in comparison to the other existing techniques. Now, another group proposed MobileNet V2, another group proposed ResNet 50. So now if you go to Google, download the original paper of ResNet 50, you find that what is that combination they are using, number one, and in which type of problems this particular algorithm seems to be better. Now, once you have this already trained deep neural architectures with a complete architecture in place, now I have an application. Now what I do, I look at all these things, all these existing trained deep neural architectures. The code is also available in GitHub or MATLAB or Python. Now what I do in my application, I try to see that my application is similar to or closer to what type of problem where ResNet 50, let's say this one, ResNet 50 is working better. Now, if I say that my application is closer to those kind of applications where ResNet 50 is working better, what I do is in my application, I take ResNet 50 as such, and then I start training. Now, what if that means? I have a starting point. The starting point is the ResNet 50, and then my training will be slightly fine-tuned for my application. So I don't start from the beginning. I don't decide. I don't break my head how many layers I will take, what type of learning parameter I will take, what type of filter I will take. I will not break my head. What I will do is I will try to use the experience of some other researcher. I transfer that learning. So this is called basically transfer learning. So I use this transfer learning approach, that the learning which others have done, I just take that entire model and use it in my application. Transfer learning is basically, if I give it in a kind of a analogy, so for example, if you remember, Mahendra Singh Dhoni was not a cricketer initially. He was a goalkeeper in the football. Right, and one day many of you might be knowing, one day the coach find that the original wicket keeper didn't come, and he saw Mahendra Singh Dhoni keeping the goal post, and he asked them, today you come and play. So he came and started keeping the wickets, and he saw that he is going good, and rest of the things are history, right? So what happens is that the learning what Mahendra Singh Dhoni had in football goalkeeping, he just transferred that learning to wicket keeping. So he didn't learn from the beginning. Now this type of model, right? Your brain also has learned in some. So suppose I have learned one language. Let's say I belong to the state of Odisha. If I've learned one language, let's say Odia, when I learn another language, I don't start from the scratch. I know what is noun, what is verb, what is adjective, what is adverb, and based on that, in relation to that, I transfer the learning to learn a new language. So transfer learning is basically a learning which has already happened, doing better in some other domain or in some other application. I take that learning and apply it in my application, and that application, and then I just fine tune that. I just learn the differences. So this is how the deep learning network evolved actually. Now, so I think with this much of introduction, so what you have to do, I have to, if you want to do a deep learning, deep neural network application, if you have an application, if you have a problem at hand, my first recommendation is that look at the either Python or maybe MATLAB or maybe GitHub. You go there and you find out that what are the existing deep neural architectures available there, and go to the base paper of that particular architecture, read that paper and see that what is that paper talks about that architecture, whether it talks about how many layers, etc. And they must be saying also that for what type of application, for what type of data characteristics, this particular network architecture works better. Learn from that, and then you choose which network will be good for you immediately, and then take it in your application. If you're not working on deep neural network architecture, that means you are not supposed to design a new deep neural architecture, etc. You want to use it for your application, this is good enough. Now, I think I'll just switch over to a couple of applications which we have done. And as I told you at the beginning, these are the work in progress, and we have not yet, I mean, we have reported, but the work is yet to be published. But nevertheless, let us discuss this. Now, there is a work called, we have done some work called Sensing Without Sensors, a deep learning model for human activity detection using Wi-Fi signal. I think madam, while introducing me, he said that I mostly work on wireless communications and sensors, and this deep learning, machine learning, etc. I use it for my application, but I don't work on that actually. Now, this idea of sensing without sensor, if I go with this, so what is the objective? The objective that I will try to recognize, identify, detect the human activity. What are the activities? Whether you are sleeping, whether you are jumping, whether you are clapping, whether you are falling down, or whether you are walking. So these are your activities. And how do we detect these activities? What is the state of the art, or what is the technology available now? You have accelerometer sensors which can detect your movement in X, Y, Z direction. You have a gyroscope sensor which can detect your angular movement in all the three directions, and you have EMG sensor which will detect your bending and all these things. So there are so many sensors available. But can we also activate, I mean, detect the human activity without using those sensors? So, and what we are trying to do, we are trying to use Wi-Fi signal. What's a Wi-Fi signal? I mean, let me just take 1 minute here. Let's say there is a Wi-Fi router there in my room where I'm sitting now, and the Wi-Fi router continuously transmits signals, right? 2.4 gigahertz, that the standard way. So the signals come. Now, whenever the signal goes, whenever it gets a wall or it gets a body or an object, etc., the signal gets reflected, refracted, etc. Now, suppose I have now let's say I start with this assumption that there is a room and there is nothing in the room. It's a static room. There is nothing in the sense that whatever things are there. Let's say there is a bed, there is a fan, there is a AC, there is a computer. So all these things are there, and there is a Wi-Fi router which emits Wi-Fi signal. Now I get a Wi-Fi receiver and I collect the Wi-Fi receiver. I collect the characteristics of the Wi-Fi. Look, I'm not talking about data. I'm talking about the signal characteristics. What is the amplitude? What is the phase, etc. So I collect that. Now I level that as there is nothing in the room. So that this is my level. So I collect this signal when there is nothing in the room. Nothing means no other external object is there in the room. I collect that signal and level it as nothing. Now a human being goes inside the room and sits in the chair. Now when the human being goes inside the room and sits in the chair, the human body will start reflecting the signal, etc. So the characteristics of the signal received by the receiver will change. Now I level it as that, okay, there is a human being sitting in the chair. So this is the level. Now similarly, I do a lot of activity within the room, and correspond to each activity, I level that particular data and then use some machine learning or deep learning technique to classify them. If I'm successful, then depending on the characteristics of the reflected received signal, I can find out what is the activity of the human being going on inside that particular room. And this is mind you, I'm not using any sensor, I'm not using any wearable sensor, etc. So that's the work. So quickly let me go to this. The sensor based activity recognitions are there. You are using accelerometer sensor, you are using gyroscope sensor, you are using video cameras, so camera video analysis, etc. You are using wearable sensors like Google Watch, Fitbit, etc. Cloud and server based analysis people do. So smartwatch, Fitbit like devices, smartphones to some extent. Your smartphone will also detect that you are falling down or you are sleeping, etc. So these are the standard techniques which are already there, and people I'm not saying that the things what we do are also not there. People have started doing that also. So these are the sensor based activity recognitions. Now, what are the challenges here with the sensor-based activity recognition? Convenience. So, say you ask me to wear a belt and all these things while I'm sleeping and all these things. This is not very convenient to me actually. And I'm going to take bath in the bathroom, etc. And you want me to wear a watch and all these things. I don't feel convenient about it. Acceptability. Many people have their own perception about these devices. I tell you, we wanted to do a study with IIT Bhubaneswar about monitoring the baby health while the baby is still inside the mother's womb. So what to do? I mean, they created a belt. I was kind of helping them in the machine learning part. So what they did, they created a belt, and the belt they have to wear it around their stomach, belly, and then they will try to monitor the baby movement there. Many people didn't accept it. They didn't like it because they thought something must be radiating. It may not be good for the baby health, etc. So people didn't accept it. Affordability, many a times this cost is prohibitive, even if you accept it, but the cost is too much. Even if you want to afford, you want accept and all these things, still availability is not there. Large scale availability is still a challenge. Privacy, of course, is a big issue in these type of cases. For example, if you want camera based activity recognition, camera and such other devices are considered to be a breach of privacy. I cannot have a camera in my bedroom, I cannot have a camera in my bathroom, I cannot have a camera where I sleep, and so many things. So camera based activity recognition is there. Many people have done it and it's fantastic. But there are limitations to camera based activity recognition because you cannot have a camera at places where it should not be. So the challenge is to develop a system which is acceptable, available, and affordable. What is Wi-Fi sensing? So I've said sensing without sensors. Wi-Fi sensing is a new technology that enables motion detection, gesture recognition, and even to some extent, I think at MIT USA, they have started just recently, they have published a paper in, I think, 2020, August only, to have biometric measurements. That means they are trying to measure heartbeat. They're trying to measure your breathing rate using Wi-Fi signal. So the accuracy, etc., is still a question mark, but they have started working on that direction. There are other technologies that use radar signals, video-based, etc. We just discussed. Wi-Fi has become suitable solution because of its bandwidth, because there are free bandwidth available. It coverage, because Wi-Fi signals can travel up to 100 meters, 200 meters, etc. The one important thing is that it can also penetrate obstacles. For example, there is a wall. If I have a Wi-Fi router in my home, I can still get signal inside my room because it is able to penetrate the wall. Now, this particular characteristics is now being used to use Wi-Fi signals for through wall sensing. What is through wall sensing means? You can sit across the wall, behind the wall, and still can see what is going on inside the room actually. So why it is possible? Because I don't have that, but this is possible. I don't have that slide here, but it is possible because the Wi-Fi signal can go through the wall, and after reflection, it can come back through the wall. Now, if your receiver is your transmitter and receiver both are across the wall, that means behind the wall, still the signal can come, hit your body, and then go back. And if I can characterize, level, train that particular signal, then you can know what is going on inside the room without entering into the room using Wi-Fi signal, because Wi-Fi can penetrate the walls. And if you want to penetrate big wall, small wall, different material wall, etc., the transmission power also you can adjust. Like instead of normally 1 watt power transmission power in case of a standard router, you can make it 2 watt, 3 watt, so that the reflection, etc., you get a better signal there. So Wi-Fi sensing is possible. So how sensing can be done? Now look at this experiment actually. At least one Wi-Fi transmitter is there and one Wi-Fi receiver is there. So Wi-Fi transmitter will transmit the signal, the receiver will receive the signal. The receiver should be able to sense the changes in the transmitted signal. So when the signal is transmitted, if there are multiple objects inside the room, so many things are happening inside the room, the signal characteristics will change at the receiver end. Now the receiver end will try to notice what is the change in the signals. How do you notice? First, you take the baseline. That means you collect the signal when nothing is happening. And then when something is happening, you collect the signal. And that change in the signal characteristics will be pointing to a particular activity. So initially, the system learns the environment with no humans in it. Whenever the system wants to track or sense the human activity, the transmitter sends the signal to the receiver. The receiver receives all the reflected signals from the objects and humans along with the transmitted signal from the transmitter. So that's the characteristics. So what are the three classification of Wi-Fi sensing? What is one characteristics of the signal is that what is the received signal strength indicator? This is nothing actually. In your mobile phone also you see the signal strength actually in parallel lines actually. So you see 3 lines, 4 lines, 5 lines, 1 line. So that means that shows what is the strength. But you can get a value equivalent to that also. That's only a visual interpretation, but you can get a value equivalent to that. So that is basically the received signal strength. So when a transmitter sends a signal, the receiver is at a distance, and with a lot of reflection, etc., the strength of the signal will decrease. By the strength of the transmitting signal will decrease, and when the receiver receives it, it receives a particular signal strength. Even that will give you some information. There are more information hidden inside the Wi-Fi signal, which is known as the channel state information, CSI. So every channel will have some information hidden inside this, and that information is actually huge. You get so much of information there. You get the amplitude change, you get the phase change. I will discuss about this. The other one is also software defined radio. I will not discuss about this. So let's not talk about this. So what we will try to do now, we'll talk about this slide. RSSI, that means received signal strength, and CSI, that means the channel state, are device free. For example, I'm not wearing anything. I'm just and does not require any more installation. Why do I say any more installation is not required? Because every home, every place, every outside, every mall, they are all installed with Wi-Fi these days actually. So you don't require a separate installation there. Why Wi-Fi? Again, that's the challenge here. Since Wi-Fi is easily available in the indoors, that means offices, homes, and outdoors also these days, such a system could be built without including much cost. You don't need very cost. Affordability is a challenge actually. So you don't need much cost because Wi-Fi is anywhere there, everywhere there. That is being used for a communication. Now what we are trying to say is that can you also do it for sensing beyond communication? So Wi-Fi for communication is there, established. Now Wi-Fi for sensing. So we are not looking at the data part of it. We are looking at the channel characteristics part of it. Wi-Fi is a universally adopted standard. Cisco predicts that by 2022, there will be 549 millions of public Wi-Fi hotspots. So Cisco is predicting that there will be 549 million, 1 million equal to 10 lakh. That means 50 crore, almost around 55 crores of public Wi-Fi hotspots will be there. And that's a huge. So if you can use it for sensing, then you can imagine that what is the sensor network size? It's a huge sensor network size. So Wi-Fi hardware is produced at a lower price. I mean, you get 1,000 rupees, you get a Wi-Fi router and all these things. Now signal, and this I've already told about, the signal can pass through the walls and the other objects. So that allows me to see through the walls actually. Now I think this you can okay, you only look at the last red line here because I don't want to talk much about it. So this is a non-intrusive device-free sensing. What does it mean? It means that I don't have to wear anything. There is no device, separate device is required. You are as usual actually. You sleep, you go to the bathroom, you go to toilet, you sleep, you do whatever exercises you want to do, but still, and without wearing any watch or without anything. So this is a non-intrusive technology. And this is also a device-free technology. So this is this one. If you look at this, this is the new term actually, device-free wireless sensing. Now we don't need any sensor device. We don't want any sensor device, nothing to wear. So this technology, this term is now picking up, called device-free wireless sensing. Now, this technology has been used for, to some extent, like localization, where is the person, how many people are there inside the room. So people have used some of these applications, but activity detection, micro activity detection, etc., is something that people are coming up with now. Now, what is non-cooperative? It can work with non-cooperative. Now, what is non-cooperative? Suppose you want to do what I'm doing, you want to track what I'm doing here. You want me to wear a watch or something, then I must have to cooperate with you. If I say, no, I don't want to wear this, I don't want to do this, then it becomes a challenge. But for a Wi-Fi communication, I mean Wi-Fi sensing, you don't have to do anything. You don't have to ask cooperation from the user actually. If there is a Wi-Fi router, it will try to detect it. So compared with the state-of-the-art sensing techniques such as camera, wearable sensors, etc., DFWS does not require specially deployed sensing techniques. It can also work, I repeat, it can also work in dark and dusty environment. Camera has a problem. Light has to be there, proper light has to be there. Sensors has a problem. In dusty environment, sensors don't work. But for a Wi-Fi, light is not a problem, dust is not a problem, humidity is not a problem, temperature is not a problem, walls are not a problem. So there are a lot of advantages about that. So what I do here, I mean, look at this actually. So first, let me say with RSSI based Wi-Fi sensing, what we did, and then how do we move on actually. So received signal strength is a MAC layer protocol. It provides only coarse grain information. What is the coarse grain information? It will only tell you what is the strength of the signal you are receiving, nothing else. One number. It gives you only one number. So it doesn't give you a much detail, but this can be used to find out a number of people inside the room, etc. So this could also be viewed as the sum of strength of all the subcarriers. When a person moves, multipaths change, and RSSI value also seems to be fluctuating and may not give enough information about the activity recognition, but there are certain recognition. Now look at this. This experiment, in fact, we have done it here also. Now there is a transmitter here in a room. There is a receiver here inside the same room. Then the students, I mean the participants, the people here, they come and go. They move around inside the room actually. They come here, they come in the line, then they come here, they go there, and sometimes they go out also. So what do you do? So so this is the scenario actually. So in this scenario, there is a transmitter, there is a receiver at two corners of a room. People come in, people go out, people move around. I repeat, they are not sitting here. In this experiment, they are not sitting, they are moving around in the room. Now, if you have done that, so what we did, we took a small Wi-Fi, I mean a small microcontroller, that is ESP8266. I think you people who are using on IoT, etc., they might be knowing it. But that otherwise also it's not difficult. So there is a small controller. This is the controller, ESP8266 module. So ESP8266 module actually transmits. There is a Wi-Fi module here, so it can transmit Wi-Fi signal. It can receive also Wi-Fi signal. So that's a simple thing. So the ESP8266 module. So we have got two ESP8266 module. One we have used for transmitter, and another you have used for receiver. The distance between the receiver and transmitter is 10 meters. So inside the room we have put 10-meter distance, and within the 10 meters people started moving. Experiments were conducted using 5 people. 5 students started walking within the room, and sometimes one, sometimes two, they come in, they go out, etc. So the data is collected every 500 milliseconds for around 8 minutes. So that's what is the collection. Now look at the thing here. So what we did in the whatever RSSI values we got at the receiver end, we plotted it in the y-axis and time in the millisecond. So the time in millisecond for 8 minutes, we plotted it. So initially, look at this side. Initially, there is nothing. Nobody was there. Somebody started entering into the room and started moving inside the room. So slowly you see that the RSSI value started fluctuating. And this is the place where you are getting the peaks, etc. Right? In this area, there were 5 persons. In this area, there were 3 persons. In this part, at this time, there are 5 persons. At this time, there were 2 persons actually. So, I mean, I'm trying to say that if from the plot here itself, you can make a kind of an estimate that how many people are inside the room. So if I just put a receiver and transmitter, and the transmitter data I collect from somewhere else outside the room, I just get the transmitter data, the receiver RSSI value, and plot it. Looking at the plot, looking at the fluctuation, I can try to predict that how many persons are there inside the room and how many persons are moving inside the room. That's a more or less. Now you can say that how it is possible. Suppose people are playing inside a room and there's an indoor playing and all these things. So how many people are there? Because as I told you, if they are static, we are not able to generate it. If the people have to be moved. And when people are moving, it can be a basketball game, it can be a badminton game, etc. So how many people are? Suppose there is a badminton court and there is a doubles match. So you can say that if 4 people are moved, 4 people are there. If there are 2 people, then probably the singles match is going on. That's the idea. But as I told you, this doesn't give me enough information about to detect the activity recognition. Now what we do, we now go for the channel characteristics. Without going much into the electronics part of it, I'll just communication part of it. I'll just say that what is the data we are getting and how do we try to qualify it. Now look at this. RSSI value gives me a single data. But the channel, what I'm talking, there are in each communication, there are sub channels or sub carriers. So there are k number of subcarriers. In fact, with 2.4 gigahertz, the standard Wi-Fi router, what you have, there are 30 channels. So with 30 channel, so you can imagine that it's a prism. The RSSI value is a single ray, but the prism, that Wi-Fi channel actually gives me 30 channels. I mean, this is just an analogy. There is no prism actually, but you can visualize that each line, I mean each signal, the RSSI signal is actually consisting of 30 subcarriers, 30 channels. So these 30 channels will give me that data. Now, what you do in case of a CSI-based sensing, that's what I want to say, and then we'll go for the deep learning here. The CSI is used to capture the fine grain variations in the wireless channel. Fine grain means little variations will also be captured in the CSI value. CSI is the strength of individual subcarrier. How many subcarriers are there? 30 subcarriers are there. It contains the amplitude and phase measurements for each subcarrier. Thus, it is more informative than RSSI. The main challenge in CSI-based approach is that accessing this CSI data on commercial device is slightly difficult. And many places they say that this CSI is a private feature. You have to do a bit of trick. In fact, Intel 5300N, that's the Wi-Fi chip. It provides the CSI values actually. And in MATLAB, you get a little bit of library and all that. So with the help of CSI techniques, we can do more accurate localization, object tracking, and interference evaluation. Now, what you have to do here actually, now look at this side, left to right. You have a Wi-Fi transmitter, and these are the Wi-Fi receivers actually. So there is a person here, there is a chair here. So these Wi-Fi signals will start reflecting, bouncing off and all these things. And then you get here. Now this one, what you get the channel state information. So what is the channel state information? You get 30 information for amplitude, 30 information for the phase. Now you know there are a lot of this part. Then after that you require a bit of signal processing. One of my colleague in electronic sciences is helping me in here. What you do here, we are trying to, because there will be a lot of noise, right? Even the fan is moving, there will be noise, etc. So you do a bit of low pass filter, so the noise will be eliminated. The signal transformation can be done, wavelet transformation or Fourier transformation, etc. So now what I'm saying, the channel will be clean, the data will be cleaned, noise will be removed as much as practicable, and then you do it. Now next we have algorithms. Now these algorithms can be, you can create a model, but that's what we said, we will use deep learning models, etc. Some people use hybrid models, etc. But we have used deep learning model here. What are the applications? You can detect what is there, you can recognize what is there. Suppose I can detect that there is a human being. The next stage that can you also recognize who is that human being? Then can you estimate what will happen or how it is moving and all these things? So there are a lot of applications based on that. So what is the what is the pyramid table? You get the channel state information, you clean the data, you process the signal, you avoid the noise, and then you apply some algorithms, and then you can apply some applications on top of it. So that's what I'm saying. The same thing. So first is that if there is a null line of sight, suppose there is a wall or something, you have to have this information, because otherwise you don't know what is the characteristics of the signal. So first you have to see that there is a null line of sight. That means whether there is a wall or there is nothing between the receiver and the transmitter. What is the location where it is put, where it is deployed, whether the material, that is the wall or something that is used, is wooden or steel or something, because every material reflects in a different way. Now, so this part is the sensing environment. So the environment is whether it is there is no object, what is the kind of object, from where it is getting reflected, what type of material you are using. So all these things are the environment part of it. Once the environment is done, then you can find out whether there is somebody. Just detect where is it and what is it he or she is doing. So detecting a human being, positioning a human being or localizing a human being inside the room, and then finding out what he or she is doing, whether walking or sitting. So these things can be done. Now, let's say how the experimental was set up, what kind of experiment we have done, and what kind of learning we have used, etc. So the data that contains, so we collected data from a benchmark also here. So the data that contains CSI values for 6 activities: walk, jump, fall, clap, wave, and sit. Sit is actually basically somebody is sitting quietly. That means no activity. So this is correspond to no activity. Sit is that he is just sitting quietly, nothing doing. So experiments are conducted for 8 days with 9 participants. 9 people were participated in the experiment. So sometimes they were walking, sometimes they were jumping, sometimes they were clapping, etc. So 9 people were there, not for a single individual. And we collected the data in 8. The data was collected in 8 different days. So the data was recorded for around 1,000 trails in each activity. 1,000 trails means walking 1,000 times, jumping almost 1,000 times, falling 1,000 times, clapping 1,000 times, etc. And every time when you conduct an activity, we collect the Wi-Fi signal in the receiver for 5 seconds. And that's also huge actually. So if you look at this, the hardware, we are using a Raspberry Pi platform for signal transmitting and receiving. Open CSI platform, that is CSI means it is channel state information. Open CSI platform is used for capturing the CSI and all that. The communication was done with 2.4 gigahertz frequency. That's a standard Wi-Fi router. The transmitter and receiver in this case are placed at 200 feet. That means 2.5 meter. 2.5 meter is almost 8 to 9 feet. So in a small room, we put a transmitter, put a receiver, and within that the activity was conducted. Now this is the system, right? So you look at this side. So here we have a Wi-Fi router with 3 antennas. So this is a transmitter, TX1, TX2, and TX3. So there are 3 antennas which the Wi-Fi router has. So 3 transmitters are there. Now this one, that is what I'm saying. This Intel N5300N. So this is a Wi-Fi. It's a kind of a Wi-Fi card actually. Wi-Fi wireless access point. So this access point is inserted into this. This is the desktop actually. So in the desktop we inserted this card. So these are the receivers. So this is receiver 1, this is receiver 2, and this is receiver 3. So there are 3 transmitters, there are 3 receivers. So this is considered to be a MIMO effect actually, multiple input, multiple output. So what is that I'm having now? Inside the room, I have a Wi-Fi access point with 3 transmitters. Inside the same room, I have a computer which receives the signal with 3 receivers. So 3 transmitters, 3 receivers. Now what are you doing? So look at this. So what is the data we are collecting in that case? There are 3 transmitters, there are 3 receivers, and there are 30 subcarriers, 30 channels. That's what I'm saying. 30 channels. So 3 cross 3 for each 30. So in one frame, I get 30 cross 3 cross 3 values. Now, because I'm collecting the data for 5 seconds, so in 5 seconds, I get 100 frames. Now, I tell you what is the size of the data. The data which I'm getting is, I get from transmitter 1 to receiver 1, that's 1 pay. Transmitter 1 to receiver 2, that's another pay. Transmitter 1 to receiver 3, that's another pay. So there are 3 transmitter and 3 receivers. So there are 9 pairs. 30, because each when you receive it, in each transmitter receiver pay, there are 30 subcarriers, 30 sub channels. So for each channel I get a value. Now at one point I get 30 cross 3 into 3, because I'm observing for 5 seconds, I get 100 frames, 100 such records. So 100 cross 30 cross 3 cross 3 is one sample. So what is the size of this? 100 multiplied by 270, that is equivalent to 27,000. So 27,000 values you get. So 27,000 is my data sample size. So 27,000 values I get, 27,000 amplitude values I get, 27,000 phase angle I get, and this I have to train it for the different type of activities. Now what we did, so we observed that each activity is behaving abnormal when compared to other activities at some point of time at a particular subcarrier. That's very important. In fact, I will tell you that activity doing nothing, means just simply sitting, is taken as the reference to differentiate the other activities. Now look at this graph. Now in this case, the red line, this is the red line. The red line is basically no activity. You are not doing anything. So when you are simply sitting, the data is collected. Now what happened? The stream 1 cross 1. What is 1 cross 1? Receiver 1, transmitter 1. So that is the pair. And because I have 30 channels, right? If I plot channel 5, and when somebody falls down, I find there is a big peak in the amplitude at between this frame to this frame for the falling activity. Now this is this is manual observation actually. I observed it that okay, this is possible. So there is a change. I want to say that there is a change at a particular transmitter receiver pair at a particular subcarrier for a particular activity. So those values change actually. So we plotted this. So this is a fall activity. This is a jump activity. So when somebody started jumping, right, he will first kind of go down a bit, then start jumping up, etc. So we find that at transmitter receiver pair 1, channel 10 gives me this information. If you plot it, you get a different picture at this point of time. So this is characterized as jump. This is characterized as walk. You continuously walk inside the room. So this value is a continuously walking in the room. But look at this. This is at transmitter 3, receiver 1. So transmitter 3 is sending the signal, receiver 1 is receiving the signal, and at channel 15, if you plot it, the values, then this shows like this. So this is very, very interesting, and at the same time, very difficult to find out all these things. So all these things we have done. But then we thought, there are so much of data, how do we actually analyze it, etc. So what we did, we tried to use a deep neural network implementation. So what we did, so remember, we have 1,000 activities. Each activity is 270,000 data points. So I have 1,000 activities for each one: jumping, sitting, walking, falling, clapping, etc. So there are so much of data actually. So one particular characteristics of deep neural network implementation is that you must have volume of data that we have. Now the second part is that we try to see that can we classify the activities. So we use this, what is that? Spooling, then filter, and then spooling, then max spooling, then this all these things we have done. I will talk about that a bit. So what we did, we used 15 layers of convolutional neural network. That's what I said. We used a ResNet 50. So 15 layers of convolutional neural network, fine-tuned for the parameter for. So first we borrowed one idea, transferred one idea, and then you fine-tune the parameter for better accuracy. So we used different, in fact, what we did, we have used different DNN, deep neural network models like VGG19, MobileNet V2, ResNet 50, Inception V3, etc., and followed a transfer learning approach. The training time was quite high actually. Initially, it took almost 40 minutes for us to train for all the activities taken together, considering all the CSA values. We tried to reduce the time at the cost of accuracy also. As I told you, this paper, this work it's not yet published, but still, we are still struggling to do whatever best we can do here. So experimental results for recognizing the individual activities. Now what we did is, we thought the problem of any classification or machine learning approach is that they were trying to do all the statistical evaluation parameters. For example, what is the accuracy, what is the mean square error, what is the F1 score, what is the this. But when you talk about acceptability of the solution, a user is not bothered about what is your F1 score, what is your accuracy, what is your mean square error, etc. They want to ask things in a common man's language. For example, I have a friend, a doctor friend actually, and I told that, look, these days people are trying to identify COVID patients from chest X-ray and all these things, and the accuracy is almost 90%. Then he says that, so what? If there is a 90% accuracy, his logic was this: if there is a 90% accuracy, that means 100 people come for testing, and there can be 10 wrong, right? This side, that side. So do you mean to say that you release 10 people saying that you don't suffer, or you take some people who are not suffering and put them into the quarantine zone, etc., into the hospital, put them into the ventilator? So their contention is that as a user, we would like to say that whenever you say, suppose you look at only one part of the story. One part of the story means you take the chest X-ray and say that this guy is not suffering from COVID. And if you say that this is 99.9% accuracy or almost 100% accuracy, if the system concludes that there is no disease, that means it is no disease. But if the system concludes that there is a disease, you can say that there is a 10% error. We will go for another test. So when 100 people come for the test, I look at your system, and the system says 90 people are not suffering, so I will ask them to go home because I know that this is 100% accurate. For the rest 10 people, I will say that go for the second test because there is a chance that the system is wrong here. So he said that you have to look at false positives and false negatives. If you say no, means no. If you say yes, means yes. So don't tell me about accuracy, etc. So what we have done, we thought that look, I'm not worried about the accuracy of detecting the activities, etc. Can we do something so that, for example, my grandparents are there. If they fall down, I must get the alarm or the event notification. If they clap and I don't get it, there is something wrong with the clapping, some 10% error, fine, no issues. If they are waving the hand and I'm not recognizing in 10% cases, fine. But if they fall down, I want 100% cases that I should recognize them as a fall down. So there should not be any false negative for fall down activity. I repeat, false negative means if you are falling down and the system is not able to detect that you have fallen down, that's a false negative. What is false positive? You have not fallen down, but system finds out that you have fallen down. That's a false positive. True positive, true negative, anyway you know. So in this case, we try to change the objective. The objective is that we are not looking at accuracy, etc. My objective is that we'll try to look at that there should be false negative should be minimum as possible, and for a particular activity. So if somebody is interested for waving, so let's train the network in such a way that waving false negative will be as minimum as possible. So what we did, we trained the whole network without validation and then tested each activity separately using a program. So we considered 150 instances for each activity for testing. So we separated 150 walking, 150 falling, 100. So out of 1,000, I separated 150 of each activity. Jumping, we didn't have enough data, so we have only 90 there. Now, what is this? We got it actually with deep learning network, AlexNet, and all these things. I'm reporting the best result here. The best of all these things that AlexNet gives me: falling 98% accuracy, walking 94% accuracy, waving 92% accuracy, and all these things. But if you use PC and other things, this is the accuracy what you got, right? So you can see the difference actually. Everything is 90 plus there. Now we modified, as I told you, we modified the objective so to minimize the false negative of each individual activity depending on the requirement. So somebody may say waving, somebody may falling, and all these things. To find the trade-off between the false positive and false negative. Sometimes what happens in the process of minimizing the false negative, your false positive will increase a bit. So we have to find a trade-off. What we did, I mean, look at this model actually. The model says that, and it's not a big thing, but still, we took, I mean, I have taken 4 actually, but there are multiple models actually. So multiple stages actually. So I took a 4-stage model. Now let's say I want to find out whether it is falling down or not. That's the prediction. I don't want to miss any falling down activity. So first what I do, I give that CSI values here to MobileNet V2. If the MobileNet V2 says it is a falling, that means it is falling. I consider it's a falling only. Oh, it's a falling only. If it says you have not fall down, because I don't want to miss, maybe the other network will try to detect that it's a falling down. If it is not a fall down activity, I give the same value to the other network and try to predict whether it is a falling. So stage 1, stage 2, stage 3, stage 4. So multiple models I have taken, deep neural network models, and then we have tried to find out whether they have fall down, etc. If all the models say that no, this is not a falling activity, then I categorize it as a non-falling activity. I say no, this guy has not fallen down. My grandparent has not fallen down. So what is that I'm trying to say though? That means the false negative I'm trying to minimize. How do I minimize the false negative? Because I'm trying to see that in any case, if it is positive, I try to characterize it as a positive. So this model we have used for falling, we have used for jumping, you have used for everything actually separately. So this is the methodology. I think a multi-stage deep learning model is used for different popular models. So what are the popular models? MobileNet, ResNet, AlexNet, Inception V3, etc. The activity is classified as negative only if this is all. Only if all the models classify it as negative. Otherwise, it is classified as positive. I think this is the confusion matrix, but beyond the, you may not be able to see much here. But let me come to this particular thing. We've tried a best single model. We used one model, either Inception V3 or AlexNet, whatever. The best single model is that key. So false negative and false positive. False positive are in the bracket. False negative are in the normal things. So falling activity in case of a single model, we got 3.9%. False negative. That means what? 3.9% cases we missed that it is a falling activity. Actually, it is a falling, but you could not recognize it as a falling. False positives are only 2%. That means some other activity is detected as a falling activity. But when you use this multi-stage model, and good thing is that we could classify all there is no false negative. That means all the falling activities are classified as falling activity. False positive is 0.7%. So the whole idea is that similarly we did for walking separately, we did for waving separately, we did for clapping separately, and we found that these are the values in case of a. So everything is between one only except jumping. As I told you, jumping I didn't have enough data, and some of the data were corrupted, etc. So, but in a single model, you look at this single model, 18.6% and 7.8%. 18.6% is false negative. That means most of the jumping could not, 18.6% of the jumping activities could not be recognized as a jumping activity, whereas 7.8% of other activities are determined as a jumping activity. That has been changed, or that result could be improved to 4.4% and 3.3%. What does it mean? That means only 4% cases of jumping is characterized as some other activity. That means you missed the jumping activity. And 3.3% activity of other activities are characterized as a jumping activity. And so on, so on. Now with this multi-stage model, earlier it was almost 4 point with single model, your false negative were almost 4.8% for all the activities. It is now reduced to only 1.1%. So only in 1% cases of all the activities, we found that we are missing that particular activity. Otherwise, everything seems to be fine. So let me conclude this particular application. We presented a sensing without sensor model using Wi-Fi signals. We have used RSSI and CSI parameters to model the problem. Preliminary experiments results show that the counting number of persons and basic activity detection and gestures, we are able to do it. But miles to go actually. It has to be tested and do all these things. And if I have another 15 minutes time, or should I stop here? Hello?
Yes, sir. Yes, sir. Yes, sir. You have time.
I have 15 minutes time, right? So now let me go to another application, a deep learning framework for gesture recognition. This is also so what is a gesture? I'll quickly go through this because I just want to tell you that what we did in this case. The gesture is that I will not with COVID and other things, people don't want to touch anything now, right? You don't want to touch the lift button. In my society, there is a stick in the lift, a bunch of sticks. So I take out a stick, push a button, and then put that stick into a dustbin and all that. So we are trying to avoid touch-based control actually. So gesture is that key. So voice-based, anyway it was there, but you require a separate complete system and all that. Gesture recognition is that key through gesture. Suppose gesture means I show my hand like this. That means you go. I will not say anything. I'll just show my hand. So through your body gesture, through your hand gesture, you try to give commands. Now, can we, again, the same thing? Do I need a separate video camera? Do I need all these things? Or can I use a small wearable device using the accelerometer sensor and gyroscope sensor? I can use it as a watch or in this case, as a watch or in a finger. And using that, I will give my command to the system. For example, what we are trying to do here in this case is that most of you might be knowing this logo programming language actually. These kids in the school learn it actually, where you can draw a figure using the logo command. If you say FD40, that means a line will be drawn for 40 units. Right turn, RT means it will turn right. Right turn 90 means it will turn right 90 degrees, etc. So if I say that through my finger gesture, if I say go like this, the line will move. So I will not touch anything. It's basically are you able to hear me now? Hello?
No. Yes, sir. Yes, sir. Now we can hear.
Actually, what happened up, so I connected to my hotspot actually, but okay. So, oh my God. So it's okay, right? Hello? Hello?
Oh, sir, some disturbance is there.
Hello?
Hello?
Just please let me know because the power stuff will come in 2 minutes.
Your voice is not clear.
So, voice is hello?
Yes, sir. We can hear you, but your voice is not clear.
Just a minute because the power went off, so I have to.
Hello.
Yes, sir.
No, no, I'm asking to sir. Yes, Udgata sir, can you hear me?
Hello, sir, you are audible.
Yes, sir.
Oh, I'm sorry, actually, the power went off and all this thing. It's raining heavily here.
Yeah, no problem, no problem.
Please. It's raining heavily here, so you never know. Yes. So I'm back. Huh?
Yes, sir. Yes, sir.
I'll just share the slides again. Give me another 10
Yes,
minutes,
please.
then we'll complete it.
Sure, sure, sir. Sure, no problem.
Okay. So I think the slides are visible, right?
Yes, yes.
Okay. So the objective is to build a deep learning model based IoT framework for gesture recognition. Our main goal is to develop IoT framework for gesture recognition using this MPU 6050. I mean, this is a sensor module which measures the accelerometer, gyroscope signals, etc. And we have also used this convolutional neural network model, which is able to classify the dynamic hand gestures. So I think I don't want to talk about the motivation. The motivation is basically, instead of talking to the system or to the giving a command using pen, keyboard, or mouse, etc., we need a flexible and natural way of interacting with the system. So gestures are not only used for interacting among ourselves, it is also can be used to interact with machines, and we can also use gestures to interact with the digital world actually. So contactless entry, control of home appliances, devices like lift, keyboard, etc., is an application for all these things. So what is the existing work? Now people have used hidden Markov model, k nearest neighbor, support vector machine, random forest, etc. Different sensors like gyroscope, accelerometer, magnetometer, EMG, and acoustic sensors are also used to read the values and movements. The gesture-based interaction has been proved useful in many research areas like healthcare, computer games, this Kinect and all these things, sign language recognition, home automation, IoT control, virtual reality, and many more actually. So what we did actually, in fact, I don't want to go into the details here because we have used a hardware, and the hardware is very simple. That's what my point here is, that the hardware part is very simple. I have a colleague from electronics who helps me in that, but that is not important. The important that once you get the data, what do you want to do with that actually? So we have in fact, what I told you about that ESP8266 controller, this one, here also we are using the same ESP8266 controller, and we are using the sensor model number is MPU 6050. So this is a MPU 6050 picture, which kind of records your change in x-axis, y-axis directions, and also your rotation of the hand, right? So the motion tracking based on the MEMS technology through 3-axis accelerometer is there, and 3-axis gyroscope is also there. This is the controller actually, ESP8266 controller. It has a small controller. It has a Wi-Fi module, so it can collect the data and send to my laptop or my desktop there. The connection is very easy actually. This is, I mean, I'm saying that if somebody wants to do it, also very easy. MPU 6050 model is there, and these are the pins actually, and these pins have to be connected to these two pins. What is this? The data that is collected from movement in x-axis, y-axis, z-axis will be transferred to this. So this is basically, you get linear movement and angular movement data. Once you get the linear movement and angular movement data, so look at the right side flowchart. I read the sensor, I get the threshold, because if you are wearing it in your hand and other things, then you are not doing anything actually, because if you are not doing anything, no gesture, it will not do anything. But once you start showing a gesture, so it will start recognizing that this is the starting point of the gesture, and then it starts recording the data. So we record the data for some 3.3 to 3 seconds actually. Then we extract the features here. We didn't extract the feature because we extracted the feature for the other SBM and other things, and then we classify the gesture using the deep learning model, and then we take an action. For example, I show 7, then it will take action for 7. Suppose I want to go to 7th floor in a lift, I will show 7, the lift will take it to the 7th floor. So how do we collect the data? We are using total 6, not features actually, 6 variables. They are not features, they are variables. Linear acceleration, that means x-axis, y-axis, z-axis, and angular rotation in all the 3D axes actually. The gesture window is compared to W consecutive frames. What you have taken, like in the previous case, we have taken 100 frames. Here we have taken 54 frames. Why 54? Because the 54 is required. 54, because if I say I write 7, right? So when I write 7, I get a series of data, change in x-axis, y-axis, z-axis, and change in theta x, theta y, theta z. So I get almost 54. In some cases, it is little less than 54. In some cases, it's little more than 54. But 54 on an average seems to be good. What is the 6? The size of the number of variables are 6 here. 3-axis acceleration and 3-axis rotation. So total dimension is here 54 into 6. So 54 into 6 you get for one thing. And then what you get, now how the data is collected, 10 individuals, 10 students are there. All of them are male. Actually, it's a master's project, actually, MTech project. So that guy used his 10 friends. All of them are male friends. And they are between 21 to 30 years of group in University of Hyderabad only. So the entire data set is collected, I repeat, using right hand only. There were no left hander actually. In fact, that's what I said, it is yet to be published, this type of work actually. The number of samples collected from each individuals are not same. Somebody gave me 100 samples, somebody gave me 30 samples, somebody gave me 50 samples. So it's not completely from the same individual. Data set is collected using trigger with window size of 54. Delay of 1 millisecond is used between the frames. So one frame, then I delay 1 millisecond, then I take the second frame, so on and so forth. 16th, okay. How many? What is my idea? My idea is that I want to gesture 36 classes. What are the 36 classes? I want to symbolize digits 0. I put a hand circle, so that becomes 0, 1, 2, 10 digits and 26 alphabets, A, B, C, D. So I want to give a command to the system by gestures. The gestures are not go, come, etc. The gestures are either alphabets or digits. So 26 alphabets plus 10 digits. There are 36 classes. Each class consisting of 300 samples. So I have a data set of now 10,800 samples. And each sample consisting of 54 into 6 sizes. So this part I can leave it, because segmentation I'm not doing much, because I just try to start from where I'm starting the gesture and where I'm ending the gesture. Ending the gesture I'm not doing, because I'm taking 54 units. So I keep moving it actually. The moment I detect that a gesture movement has started, from there I'm taking 54 frames. Now this part. So the gesture classification algorithm, if you look at this, we have also used same thing, the same convolutional neural network, CNN algorithm here. Now the algorithm here, now look at this. We have used how many layers? Input, convolution neural 1, then max pooling, then convolution neural 2, then max pooling, then flatten the item, then we moved some of the windows. Dropout is a technique by which you can still drop some of the neurons because you want to reduce it, and then but the performance doesn't degrade. So that's what it is. So CNN is a famous deep learning architecture for classification. We've already discussed that. So a series of convolutional pooling operations followed by a number of fully connected dense layer, that becomes your thing. I think I have already discussed at the beginning of the talk that we have used this technique. So here we have used a 3x3 filter. The filter is 101, 011, and then 101, etc. So I get this kind of a thing. Oh my god. Then I have used max pooling. So max pooling, I think 2 by 2 max pooling only. So this 1, 1, 5, 6 becomes now 6. This is the maximum in this particular unit, and then so on. So in some of the cases, in fact, which I didn't discuss and I want to discuss here, because that's an implementation issue. as I told you, right, some digits or some alphabets are very small, very quick. For example, 0 I write like this, but if I have to write 8 is almost 2 zeros. So what we did, the size of the data what you are getting are not uniform. So we used a term called padding. What is padding? If the number of frames or number of the matrix size is not good enough, then I added 0 number of rows or 0 in the columns. So I added one column padded with 0, or I added one column padded with 0. So look at this. So I added 0 here as a row, I added 0 as a column. Why I'm doing this? Because if the matrix size has to be uniform for all the inputs, if they're not uniform, then I've made them uniform by adding 0 padding there. So this is the configuration. In fact, it's not much of an interest, but we have used 32 filters, 3x3 kernel, and this is a standard. Again, I told you, I used the transfer learning approach because we used an existing deep neural architecture and then fine-tuned it actually. Just a minute. I mean, look at this. This is a small video. So this one, I mean, it's in the development stage. If you look at his hand, that's where the device is. It's directed. Now look at this. He is signaling 3, and the system is recognizing as 3. He's signaling H, but the system is recognized as 4. That's the wrong one. Again H, signal recognized as a H. This is X, but the system recognizes the Y. So he repeated it again. This is Y, Y. Now I repeat, there is no video here. This is only the direction change by hand, and this direction I continue to recognize it. There are some mistakes and all these things, but okay. Okay, this he did during lockdown at his home. So there are some noise in the background. It's not in the lab actually. Look at the laptop actually. The laptop is continuously learning and testing the system actually. And this U or R, etc. What I'm doing, it's a video editing actually, because in the laptop it recognizes as a U, but you will not be able to see. So you have just put it here. Okay, what is that? What is the gesture he is showing, and what is that the laptop or the system is recognizing? Okay. Now, so what are the results we have got here actually? As I told you that we try to do it as fast as possible. So we thought we'll use very limited data set and try to recognize it actually. So we started with 10 samples, we started with 100 samples, and we continued up to 300 samples. So with 10 samples means 36 classes. Each class has 10 samples. So this is only 360. If you take 100, 3,600. If you take 300, it's 10,800. So what we have done, we have used this 80%, 20% training testing kind of a thing. We removed 80% for training and 20% for testing. So if you look at this, when we wanted to only recognize the digits, right? If I wanted to only recognize the digits, then with 100 dataset means 10 samples for each digit. 1, 10, 2, 10, 3, 10, etc. So accuracy was only 50%. There is nothing that we can do. So deep learning didn't work even here. But when you take 1000, it becomes 96.6%. When you take 3000 dataset means 300 into 10, 300 samples for each digit identification into 10 digits. So 3000, the recognition rate becomes 98.67%. The same thing we did for alphabets. Look at the first table. Alphabets, if you 26 alphabets, if you take 10 individuals, then the accuracy is 64%. There are 2600. If you take 100 of each, then the accuracy increased up to 98.42%. With 7800, the accuracy went up to 99.29%. Now I tell you, the alphabets gave better accuracy than the digits, because some of the digits are actually, for example, when I'm writing 3 and 8 looks same. 0 and 8, 1 of 8 looks same. So there was some confusion, but otherwise alphabets gave better result. There is one issue here: alphabet 0 and digit 0, they are same actually as far as gesture is concerned. So what we did, I mean, in this experiment, what we did, alphabet 0 we wrote it as a clockwise direction, and digit 0 we wrote it as a anti-clockwise direction. But that's a constant actually. So results of digits and alphabets taken together, the video what you saw there. So if you take digits and alphabets together, if you take only 10 sample sets, the result was 59%. 3600, the result was 97.78%. 10,800. That means 300 samples for each digit and alphabet, 36 classes, so 10,800. The results were coming out to be 98.52%. Now, what is the total result actually? Because as I told you, right, if you look at this, to test the final system, once it is trained, we collected another few, we asked a few other students to give some gestures. So we collected some real-time 80 gestures. They came, showed some 0 here or showed some 1 here, and they went. So we collected some 80 such kind of a thing. But I tell you, the problem with this is that first is that you have to find out whether this is the starting point of the gesture and this is the end point of the gesture. In 5 cases, we missed, because the student, we missed that we could not recognize that it's a gesture itself. Once you know that it's a gesture, then you can classify. So that adaptive threshold algorithm or segmentation of the gesture data, that we could not do for 5 cases. So out of the 8, 5 we could not recognize as gestures. But out of 75 gestures, system is able to classify, I mean the deep neural network architecture is able to classify 74 gestures correctly. So once you identify a gesture, then classification becomes quite accurate actually. But still the challenge is that how do I start how do I mark the beginning of the gesture and end of the gesture? At some point of time, we are not able to do it properly. So gesture segmentation accuracy is only 93.75%, because 75 out of 80 is 93.75%. Gesture classification is 98.67, because 74 out of 75 is 98.67. Overall system accuracy is that out of 80 gestures, we could recognize 74 gestures correctly. That is 92.5%. As of now, there is a device called Gesture Keeper. Gesture Keeper is a based system on real-time data streaming for controlling IoT devices. It's a commercial product kind of a thing. They designed their own sensor, they designed their own system and all these things. But still, if you want to see Gesture Keeper work also, the Gesture Keeper, I think it's a reported result actually. So what they have done, they have used this segment hidden Markov model actually. Hidden Markov model. So in the hidden Markov model, their accuracy is 87% for gesture segmentation. And once it is segmented, the classification is only 97.89%. But if you look at in the deep neural network architecture, we have used a standard IMU sensor. We have not designed our own sensor, etc. We have used adaptive threshold algorithm for gesture segmentation and convolutional neural network architecture for gesture classification. They have used only 12 classes, right? They have used only 12 classes, 12 because they are using go, come like this, but they have used 36 classes. So these 36 classes are much more complex actually. Their window size is 125. They are using a bigger data size. We have used only 54 data size, and still the results are still better. That shows that deep neural network architecture works better than the standard hidden Markov model or SBM, etc. This is, I think, I mean, you don't have to. There are 36 classes, rows are there, 36 columns are there. This is the confusion matrix. I just want to zoom it a bit and show you that, look, in most of the cases, it is 100%, right? 100%. One means 100%. The same 0 is recognized as 0, 100%. 1 is recognized as 1, 97%. So most of the cases is 100%. Only in some cases it is 99% or 96% or something. So this is the confusion matrix. So let me conclude. So we found that CNN works better result for classification if the data set is big enough. That's what is the conclusion. If you take 10, 30, 10, 100, 300, etc. As I told you, the dynamic gestures to represent digit 0 and alphabet 0 are similar. I mean, we cannot say 0 is different and O is different. So which can be handled by changing the alphabet 0 to opposite direction. Opposite direction means anti-clockwise and clockwise. But that's also a big problem. We proposed adaptive threshold setting algorithm. This is in fact a new algorithm to do it. So this can continuously real-time data stream can be classified as a gesture or not gesture, and then we try to classify the gesture. So the final accuracy is around 92.5%. And I would like to say there are still a couple of challenges which I didn't mention it here. Left hand, right hand is an issue. Then old man, young man, kid, it's an issue. So a lot of challenges, but if you collect a lot of data, I mean, it's just a master student just completed its experiment and all this. We are still working on it. In fact, we have not yet reported this paper. Results are still preliminary. So with this, I would conclude this. So these are some of the students who have been working on these type of projects: Ajit Sahu, Shruti, Sumaya, Mutunjay, and Pragya. Thank you very much. Okay. So with this, I conclude my talk. And if you have any questions to ask, or maybe you can ask me. But as I told you at the beginning, it's a little bit of deep learning. You might have learned deep learning quite a bit, but I used deep neural architecture in my application, and these are the two applications we wanted to present here. Okay. So because I'm done.
Yes, yes. Any participants, if you have any questions, please ask.
Hello, sir. Good evening.
Yeah, very good evening.
Sir, I want to know, like you said, for gesture recognition, the person have to move his or her hand in a much wider, or he can just move his hand with a short, and the area should be larger or smaller.
Sir, I could not hear it. If somebody can.
Sir, he's saying that do the gestures need to be large or big gestures, or just having short or small gestures will be enough for the gesture recognition model?
Okay. See, as I told you, this is a preliminary work, and in the sense that usually I told you, right, 54 frames actually, and if it is plus or minus 5% here and there, that's okay. But if it is too large, suppose I give a big hand like this, right, this system will not be able to recognize. So what you are doing is that in a normal circumstances, the way you, suppose I want to show 7, I show 7 like this. But if you say 7 like this kind of a hand, it will not be able to recognize, because there is a time frame attached to it. The time frame can vary 10% here and there, so that I can do padding or truncating, but beyond that it doesn't work. So I don't have to give a huge shift in the gesture. Normal gesture will work. Can I look at something? Yeah, there are some chat box. Let me open it.
Hello, sir. I have a question.
Please.
Yes, sir. The method you used to minimize the false negatives in the Wi-Fi experiment, can we use the same method in machine learning using an ensemble of models to minimize false negatives?
In fact, that's what we are doing also now. I didn't, because that is a standard machine learning model, so I didn't present here. In deep neural network, I presented the same model we are also using now. So what we are doing here is that we take some, let's say, it's a kind of, I think you might have read those papers actually. It's a pipeline of methods, right? So the methods are in the pipeline. So you can say that, the output of pipeline 1, if it is acceptable to you, accept it. Otherwise, you go and test with the pipeline 2. I can give you another analogy. Suppose I am suffering from a disease. I go to a doctor, right? The doctor said, "Oh, you are suffering and you have to be operated." I don't believe him. I go to a second doctor, third doctor, fourth doctor, right? And if every doctor says that, 3 doctors say that, no, you have to be operated, I get operated. But before that, I want to check with multiple doctors. So this is almost the same model. We want to check with multiple models. And if the model is saying, every model is saying that it is negative, then only it is negative. This, in fact, I saw we are also part of that actually. There is one paper where you say COVID testing, right? People use chest X-ray and all these things. Now, suppose you say there is a person who is actually suffering from COVID at this point of time, and you recognize it as a negative. Now, once you say you are negative, this guy will go back to his home, celebrate, do partying, move around, etc. And in the process will infect another 100 people. So what you are saying that if somebody is a false negative should be less here. What does it mean? It means that if somebody is COVID positive, he cannot be left. He should be identified as COVID positive only. Because even if a COVID negative person is identified, that's okay. But you cannot leave one COVID positive person as non-negative. So there we want to reduce the false negative. So what do? You go for multiple type of testing. If one test says that you are positive, you are positive. So this model, as you rightly said, this model can be used for standard machine learning. It's a pipeline model actually, multi-stage pipeline model. You do this depending on your application, whether you want to minimize the false positive, whether you want to minimize the false negative, whether you want to minimize the whatever you want to minimize, depending upon your requirement.
Okay, sir. Thank you, sir.
Thank you very much.
Sir, good evening, sir.
So can I ask a question?
Yes, ma'am.
Yeah, it's more of a curiosity than actually related to deep learning, because see, a lot of sensors have been developed where they're using temperature or infrared radiations, but it seems like you are using Wi-Fi and you are getting a very high accuracy. Although we can increase the accuracy at the level of deep learning model, but then how do you ensure that the Wi-Fi connection won't break in between, right? So I'm just curious, like if you want to sense the movement on borders, something like which is a very high security issue sort of things, then Wi-Fi is not something where you can ensure that the signal will be continuous and won't break. So although you can achieve the accuracy at a very high level in the modeling, but then in the initial input level, it's again limiting, right?
Yeah. First, let me say that I agree to your point. But let me tell you also that the Wi-Fi what you are using here and the Wi-Fi what you are visualizing, the Wi-Fi disconnection, Wi-Fi disruption happens at the data communication level normally, right? So we are not talking about data communication. So if I have a Wi-Fi, for example, during this talk, in my connection left because of the power connection, but if a Wi-Fi is on, it will emit signal. And we are not worried about whether it is connected to the internet or not, whether it is connected to the some server or not. We are not worried about that. I'm only worried about whether it is transmitting signal or not. Mostly, 99.999% cases, Wi-Fi will continue to transmit the signal. It will not stop transmitting the signal. That is one. The second part is that which I didn't talk in this slide. It has another part of it. There are two types of sensing. One is called active Wi-Fi sensing and passive Wi-Fi sensing. In an active Wi-Fi sensing, the Wi-Fi router is already in a passive Wi-Fi sensing. The Wi-Fi router is already there. You come with your receiver. The Wi-Fi is being used for something else. You sit quietly at a corner and collect the data and characterize. That is passive Wi-Fi sensing. The active Wi-Fi sensing is that you go with a transmitter and receiver as a kit. So suppose I know that there is a terrorist hiding inside a room, and in fact, US people are trying to do that in America. So the military people will go with their equipment. They send a Wi-Fi signal that will penetrate the wall, go inside, and then hit the body there inside and out, and then come back. Then they characterize that Wi-Fi signal at receiving end to find out whether somebody is there inside the house or not. So in this case, in this application, there is no there is no chance of failure of getting the signal. And again, I repeat, failure is always there in every system. And the experiments which we conducted or the results what we are shown, they are extremely under controlled environment, right? Inside the laboratory, a student comes in, sits, goes. But when you deploy it in the system, there is a lot of challenges. And I also tell you that we don't have. This is a new area of research. Very few people in United States and one guy in University of New York, they have started working on this. This work which I presented, actually it is inspired by the work from MIT. Actually, MIT people have started working on this, and miles to go. Yeah.
Thank you very much. It's very interesting, and thank you for sharing your expertise with us.
Thank you, madam. Thanks for saying so. Yeah.
Good evening, sir.
Good evening.
Sir, if suppose I'm going to design a CNN architecture, in what basis I can select the total number of layers is required for my data sets?
Yeah, that's what I told you, right? That's the transfer learning. It's very difficult. It's very difficult to find out how many layers will be there, what filter you will use, and all these things are very difficult. I suggest, if you're trying to do that, I suggest that first you read some of the existing architectures which are already there. For example, VGG 19, ResNet 50, MobileNet, Inception V3, AlexNet. There are so many networks, so many architectures are available. Go to that paper. In that paper, they mention how many layers they have taken, what type of filter they have used, etc. And they also have reported what kind of data set works best for that kind of an architecture. And they characterize that data set also. If you feel that your application and your data matches with the characteristics of that data, please go ahead and use it.
Okay, sir. Thank you, sir.
Thank you. Yeah.
Excuse me, sir. I have a question. Can I ask?
Yeah, please.
Sir, with respect to the first research article that you are presenting, regarding the
Wi-Fi sensing.
Wi-Fi sensing. So,
yes.
in that case, you have used multi-stage model, right? So, you have
Yes.
used lots of you have used lots of architectures. Does it not appear to be an over parameterized network? So how did
Okay.
you handle in that case?
Okay. As I told you, initially I didn't use multiple networks or multi-architecture, etc. I used only the best architecture based on those things. But then we realized that, okay, what is that you are doing actually? Getting accuracy is not good enough. I said that, okay, look, my application requires that, okay, for falling activity, I should be able to detect it 100% cases. I don't mind jumping, waving, clapping, etc. That's not my point. So we used a multi-tier architecture there, or multi-stage architecture here, so that I don't want to miss any falling activity. Now now the next question comes that, okay, how do you train them and all these things? They're all already trained. They're all already trained offline, already done. During the deployment, let me tell you, during the testing, a set of Wi-Fi signal characteristics come, and I characterize whether it is a falling activity or not. That's it. And it doesn't take time. It's just microsecond, milliseconds. It doesn't take time. So your question is correct. If you want that, if there are multiple architectures, then multiple fine-tuning of the weights, millions of weights, will take a lot of time. But that is done offline. That is done offline. In a server, we train it. Once it is trained, in this system, when you are testing it, it's just one sample and the network is ready. And I tell you, the arrangement of the architecture is such that most of the cases, most of the falling cases will be identified by falling by the first model itself. Only 5 to 6% cases will go to the second stage. From the second stage, only 1% case will go to the third stage. So it doesn't affect actually. It doesn't affect the performance, because very few will go to the second stage, third stage, fourth stage, fifth stage, etc. And they are worth. I mean, you should do that actually.
No, sir. No, sir. What I meant was you're trying to overfit to the particular action called fall. So, are you just trying to do that?
Yes. You are
So
correct. We are trying to overfit. We are trying to overfit a particular activity called curve. Yes, that is true. But you see, overfitting, if you have understood, overfitting is for the training. You are overfitting for the testing. We are not doing overfitting for the training. We are doing overfitting for the testing. Training is simple. Training, we are not compromising on anything. Training is a normal training, independently trained, and the way you should be trained, you are doing it. So overfitting is normally used for training. So the network will be trained and overfitting for the graph. So that we are not doing. We are doing only for the testing. So while we are testing, we don't want to miss a falling activity. That's the challenge actually, nothing else.
So I have another question. In the gesture recognition, there is, it might happen that the coincidence between the alphabets and the numerical, say for example, 3 and B and 7 and Z are, the gestures are almost same. So how did you handle this?
Yeah. That's the problem actually. There is a problem. There is a problem like this. As I told you, one example is that alphabet O and 0. You don't have. There is no distinction. There is no distinction between these two as far as gesture is concerned. So similarly for 3 and B, for left hand and right hand. So there are issues. So right now what you are trying to do is that mostly, and in fact, if you have noticed that the student, when he was doing an exercise, when he was doing digits, he was bringing the hand from top to bottom, and for alphabets he is doing from left to right. So something like that you can do, but otherwise it still remains a challenge actually, because every human being are different, everybody is doing differently. So what you are trying to do is that there will be a training phase for each body. Suppose you want to use it, so for few you have to do your alphabet writing and digit writing, digit gesture for 3-4 times, and then the system trains automatically after that. So this is the model that we propose, that it requires a user level or individual level training, maybe for a small time, but it requires a user level training also.
Sir, good afternoon. Sir, good afternoon, sir.
Very good afternoon.
Sir, the already architectures are available. Already so many architectures are available.
Yes.
With that architectures, can I use that architectures and apply any one of the application? Is it become a research problem, and can I move for the publication?
I could not hear. Can anybody help me? I could not hear properly.
Sir, one more time, sir. I am asking the same question. Sir, already existing architectures are available in the CNN. With that architectures, if I generated any application.
Okay, got it now. Now you are saying already architectures are available. If you use an architecture and just apply an application, is it good enough for a publication?
Yes, sir. Yes. Sir.
Yes. Now the question is cannot be yes or no. Where you want to? Oh my God.